Hello, welcome to my video on multi-view stereo reconstruction. This is an image analysis technique that takes a series of photos and uses those to automatically reconstruct a 3D model. It's a very powerful tool which has many potential applications, for example in engineering, architecture, video games and remote sensing. In this video I will demonstrate an example in applied geoscience. Multi-view stereo reconstruction is a technique that generates 3D models from a series of images. It's also sometimes called structure for motion. For this example I will use the software Agisoft Photoscan3D, which is a commercial tool for which very affordable academic licenses are available. The example is from a project where I visited the Beishan region of the Gobi Desert in China. I went there as part of the Great Exchange. If you want to use this technique to create a 3D model of an object, you need to take a series of photos. The photos should be taken from different angles, but should have some overlap with the other photos in the series, so make sure you take plenty of photos. In the case of the shell in the picture here, you would have to take pictures all around it, and if possible also from above. You're not limited to simple objects. The software can also capture larger scenes. The software works best if you use a camera with a fixed focal length lens. A wide angle will record a large area at once, but because of that not much detail, a telephoto lens will record a lot of detail, but will require a very large amount of photos. A normal or somewhere near that focal length lens tends to work really well, so say about 35 to 50 millimeters. With a compact or bridge camera, I would try to approach the typical 50mm equivalent focal length. Usually that's somewhere zoomed in a bit from the widest setting. But the software is really robust, and it even works with fisheye lenses, like the ones you find on small action cameras like GoPros. Which is great because GoPros are handy to attach to your quadcopter. The software will also use these photos to texture the final 3D model. So you want to make sure that all the photos are shot in similar light, so you don't get any strange color changes. When you're working outdoors, this means taking the pictures quickly, so the brightness and the color of the light is not affected, for example by clouds moving over, or by the light changing color during sunset. If you're working indoors, you want to work with nice soft lights, so you don't get any harsh shadows anywhere. One way to do this is by using natural light coming from a window. That's often quite soft. Or you can bounce the light from a lamp against the wall or ceiling. That tends to make it much softer as well. In most cases I would recommend against using a flash, as these tend to give very harsh shadows, and objects close to the flash become very bright, and objects further away tend to get very dark. One exception would be outside in very harsh sunlight, for example during a day at the beach. Then a fill-in flash can be used to lighten up shadows. This is really easy. You just pop up your flash and the camera will probably do the rest. After you have taken the photos, you need to process them with specialized software. Here I'm using Agisoft Photoscan3D, as it's a tool that works really well. Several other tools also exist, some free, some commercial. For example, Autodesk has a free program called 12-3D Catch app that works really well. The first thing that these programs do is search for points it can recognize. In the two photos below I've added some colored points to illustrate this. Please note that these are points drawn by me. They're not necessarily the same points the software would pick. The software looks for corresponding points on the different images. Once it has found these, it can use them to determine the relative locations of the camera that took the photo and the position of the points in space. With the initial points in place, the software knows the basic geometry of the scene. It can further improve the geometry by adding more points in between using stereophotogrammetry. In the software this is referred to as building a dense point cloud. In the figure below I've added the gray points in between the original colored points, and as you can see this strongly improves the accuracy and detail of the reconstructed geometry. Again, the gray dots here are just example points added by myself to illustrate the process. The software tends to find many more points. With the dense points in place, the software can construct a mesh to represent the surface. A mesh is an approximation of a natural surface made out of small triangles. You can see the mesh offered for the model of the Balinese statue on the left. I only used 4 photos for this, so it's not very detailed. The software can also project the original photos onto the 3D mesh to create a photorealistic texture. This adds an incredible amount of detail to the model, as you can see on the right. Certainly for geoscience applications, this offers great possibilities. On the photo textures we can see fine details such as fractures and thin beds. With the 3D model you can interpret these structures in 3D, and it's possible to export these models to 3D geological software such as 3D Move. For the great project I visited the University of Nanjing. Together with researchers of the University of Nanjing, I traveled to the Beishan mountains. These are located in the Gobi Desert in northern China. This area is of interest as the Chinese government is considering the construction of a radioactive waste repository in this area. The site we studied is located near the Pushpin. As you can see, it's about 70 kilometers northeast of the nearest town called Yumen. To get there we drove through the deserts, through a very large wind farm, which is currently the world's largest wind farm. Already on Google Earth you can see that this is a highly heterogeneous rock mass, and the rocks are cut by many faults and dikes and fractures. And as you can see, Google Earth provides a wealth of information, but on the finer scale is not very detailed. This house here on the top is probably about 20 meters long, so we can see some larger dike structures like this. This might be a dike, this might be a dike, but other than that we can't really see much, so we need to study the area in more detail in the field. Here you see a photo of an outcrop I studied in more detail. At the outcrop we can see the heterogeneity of the rocks even better. It is visible that the rocks have experienced several episodes of deformation. In addition to a metamorphic fabric, several generations of dikes, faults and fractures cut the rocks. The folding ruler in this picture is 2 meters long in total and folded in the middle. The light-colored structures are felsic dikes. This was a reconnaissance field trip, so I quickly collected some detailed observations on these structures, but given the limited amount of time, there was no scope to map out a wider area. So to be able to get some more data, I opted to take some photos from the well-exposed pavement. I climbed a small hill, and from there I took pictures all around me. I repeated this from several other spots. I knew I would later be able to use multi-view stereo software to correct for the distortion. This is far from an ideal approach, but the software is pretty robust and deals with it well. Taking aerial photographs would have been even better, but I had no quadcopter or balloon with me, so I had to make do. I will now show how to process these images with Agisoft Photoscan. This is the main interface for Agisoft Photoscan. The first thing we need to do is to load some pictures. There are 2 options for loading pictures. The first is through the workflow menu with the Add Photos option, or you can just drag them in from the Windows File Explorer. So let's do that. I've saved my photos in this folder. Let's have a look at some photos. Here you see the typical rocks of the Beishan area, cut through by many generations of dikes. And we can simply select them all and drag them into Photoscan. The software takes a while to load all the photos, but once they're there, They're all in here. I can look at the photos by simply double clicking on them. I can close them again. And once we have the photos, we don't really need to do much ourselves. There are options to do that. But the first thing to do is to go to the workflow menu and choose Align Photos. Here we have a few options like the accuracy and the pair pre-selection. I don't have any pre-selected pairs, so I just think about accuracy. As this is just a demonstration, I'll leave the accuracy on medium and click OK, and the software gets to work. Most steps in Photoscan take a fair amount of work, depending on your computer. Once Photoscan is done with the initial detection of the points, you will see something like this. You will see a number of dots floating around in space, and you can rotate these things around. And it will give you, if you look at it, some basic idea of what the geometry looks like. But you can't see very much in here yet. And you'll see these blue squares floating in space, and these are the locations of the photos you've seen below. For example, you can select a photo like this, and the plane will light up in there. So you know the software thinks that photo was taken at that location. And this looks roughly right. I think the scene is upside down. If I turn it over, I can see that there are a few places from where I took pictures around me. This is probably the little hill I used. Overall, the geometry suggested by the points looks roughly alright. It corresponds to the scene I have in mind, a sort of flat pavement. If you want to have a quick check of what it looks like, you can go to the workflow and do build mesh and just make do the lowest possible to make a quick preview. Now we have a better idea of what the scene looks like. The steep walls don't look very realistic, but that's probably just an artifact, and we can delete those later. The next thing to do is build a texture. Again, just do something, keep things simple. Let's just leave it at 4000. Let's make it lower, let's make it 2000 to make the whole thing quick. And when it creates a texture, it looks at the photographs and it tries to project the photographs onto the mesh surface we have made. That looks pretty good already. There are some problems there, and we can see that the steep walls are actually where it tries to incorporate the sky. But overall, yeah, the geometry sort of makes sense. You can see that there's the little hill I stood on with the sort of valley around it, and we can already sort of recognize basic structures. This here is probably a dike cutting through it. We can zoom in, and we can see that there are problems with this model. But overall, it looks already quite useful to get an idea of the scene. So this is a very rough first draft, but it tells me that that photos for this scene will work, and that it's worth calculating a more detailed model using the built dense cloud. Now that I know that the scene will work, it's probably worth calculating this at a higher quality. Just clicking OK, and the software gets to work. Building a dense point cloud typically takes a long time. Now it suggests it's going to take 1 minute, but it will probably increase, and it will probably last about an hour. So let's fast forward through this. So it took about an hour, but now the software is finished reconstructing the dense point cloud, and already You can see the dense point cloud here in space, and it looks much better than the initial point cloud. There are some places without data, but overall we can already detect the scene. So let's zoom in a bit. And it's already much better than the textured model we had before. You can see you can start to recognize many features. You can see a dike here and a dike here, and many small dikes running right here. We can see some artifacts. We can see, for example, this has a different color. So I probably used a picture which I took a bit later than the earlier models, earlier photos, and the sun was already setting. Alright, so we have a very nice dense point cloud, and we can use this dense point cloud to create a nice mesh, which will be much better than the mesh we made using the initial point cloud. So let's build mesh, and in this case we have a few options. We can make an arbitrary mesh or a height field. A height field is a very good choice if you're working with a simple topography where for example a mountainous landscape, but it doesn't really work with structures, for example overhanging rock formations or houses or things like that. But in this case a height field will work just fine. Let's use the dense cloud as our data source and face count. Let's just put it to medium, that should be good enough. Okay, let's put it to work. And depending on the complexity of your point cloud, this can take quite a while, but it seems like it will only take 20 seconds here. Oh, now it's 37, so let's fast forward. Alright, and here we are again. The software has just finished creating the mesh based on the dense point cloud, and as you can see, it's a much more detailed mesh with lots of fine structures in there. Some of these structures are really reflecting of the geometry, but you also need to be careful with artifacts, especially a scene taken from just a few photos standing on the ground. But you can see the basic geometry is right. We can see the little hill I stood on over here, surrounded by a small valley. We can't see much on this mesh itself because it's not textured. For each new mesh you make, you need to make a new texture. If you want to see the original dense point cloud we had previously, you can switch to that view with this button here. Similarly, you can see the original point cloud with this button, and you can see a shaded version of the mesh where each point on the mesh gets the color, a color taken from the photo, but not as much detail as the texture. A solid version or a wireframe version. To make this scene more interesting, we can calculate texture. We go to the workflow menu and we choose build texture, and then again we have a few options. We can use a generic texture or an ortho photo or an adaptive ortho photo. I will not discuss the last two options. Generic tends to be slower, it takes up more space, but it has the advantage that you can spread out your texture over multiple files with this option here, which is good if you have only a limited amount of memory. And this process can take a lot of memory, so the ideal is about 32 gigabytes of memory. So if you have less than 32 gigabytes, this machine has 8 gigabytes. Then spreading your texture over several files is a very handy option. Alternatively, you can make an ortho photo, which is just a texture seen from above, which tends to be more efficient, but you can't spread it out over multiple files, so you would need to increase the resolution here. Or an adaptive ortho photo, which is similar to an ortho photo, except that for steep areas such as cliffs, It doesn't use an Ortho Photo which is projected from above. In a normal Ortho Photo you would not get much detail in cliffs. So for those scenes, adaptive Ortho Photo or generic is much better. In this case I think I'll go for generic, and I'll put this to 5000, and let's make about 5 of these textures. Let's put the computer to work. And again, this will take a few minutes for the computer to process, so let's fast forward. Alright, so Photoscan has finished building the texture for the detailed mesh, and as you can see it looks a whole lot better. Let's take a closer look. You can see many small features. We can see these light colored dikes running through it here. There is some kind of darker dike running through it here. There's lots of fractures to be seen as well. It's not a perfect model because it's taken with pictures which I took while just standing on the surface. So especially the areas further away are not as nice as what you would get if you would take a quadcopter or a balloon, something like that. Still, you can see a fair amount of detail. I can use this to really expand upon the detailed fracture I created at one side. I have a much more more statistically relevant data set. Alright, so that's about it. Yeah, so this is basically the steps in the workflow. Other options that might be important are in the tool menu. The mesh, there's the option to decimate the mesh, or to smooth it, or to close holes in it. There are options for exporting a number of things, for example the texture, and there are options for which you can use to remove objects. For example, if there's a person in a photo, you can select those the people in the photo and remove them first before building a texture. And there's the option to save the file and to export the points, export the model, or upload the model. A very nice option when you choose export model is to export to a PDF file. These PDF files can be read by almost anyone, but they will contain the 3D model in a bit less detail as what you see on your screen here. But it's still a very simple way to share 3D models with other people who would probably not have more advanced 3D software on their computer. Alright, so I hope you enjoyed my video. Thank you very much for watching. Goodbye.